Axis theorem, okay? What we've already done is the z-axis being if you imagine a disc that we did in the last, or sorry, a circle or a disc, what we did in the last chapter, right? We talked about an axis going straight through this. Now that's one axis. The lamina or the disc itself can be regarded as a plane, like a piece of paper. Pieces of paper have an x and a y axis. So I could draw something like this, technically speaking. This one could be my x-axis, this one could be my y-axis, and this could be my z-axis. Okay? Now, there's something that's called the perpendicular axis theorem. Okay? So, if ix and iy are moments of inertia of a lamina about two perpendicular axes. So the moment of inertia around y is iy. The moment of inertia through the axis x is ix. Okay? They intersect at O. So they intersect at the origin, so to speak. And then the moment of inertia iz. If we want to find out what the moment of inertia is through a perpendicular axis, this axis has to be perpendicular to the other two axes. Okay? We have to prove that it's given by iz equals ix plus iy. Alright? So we're going to find out what the moment of inertia is. How difficult is it to turn it around the z-axis? If we know how difficult it is to turn it around the y-axis, how difficult it is to turn around the x-axis, then by adding them together we can find out how difficult it is to turn around the z-axis. Okay? So here's our theorem, alright? By Pythagoras' theorem, z squared, because see the way you can draw it into a z is the distance. So z is defined as the distance from the z-axis, which goes straight through the board, straight through the lamina, to the mass we're talking about. Now, what I mean by the mass we're talking about is just the chunk of mass we're examining. Okay? So this means that z is the hypotenuse. Y is the y displacement of that particle along the y-axis. X is the x displacement of that particle from the x-axis. You got it? So y is the distance from the y-axis, x is the distance from the x-axis, and z is the distance from the z-axis of this little particle delta m. By Pythagoras' theorem, because it's at a right angle, because z and y are at right angles, and so are y and x are at right angles on the plane of the paper. Okay? This means that z squared equals x squared plus y squared. Okay? Now, if you remember our inertia formula, the original inertia formula was, remember we're talking about it equals all the sums of the delta m's minus their distance, multiplied by their distance squared, the distance from the axis we're talking about squared. We're talking about the z-axis, aren't we? So it's going to be mz squared. Therefore, because z squared equals x squared plus y squared, and now we can break that up into delta m x squared plus delta m y squared. This is the sum of this is the moments of inertia around the x-axis as it was in the first exercise, and this is the moments of inertia around the y-axis as it was in the first chapter, right? So iy, and that means iz equals ix plus iy. Right? Easy enough proof. Now, regards ix, okay, I just want to bring us back to this. What was that formula we learnt off about at the start of the last chapter? The formula I asked you guys to learn off was di equals x squared dm. Okay? You can see it's just a bit, instead of talking about I, you're talking about integration of I. So that's going to be di x equals this sum of sign. See the delta m? Yeah? The delta m changes to a dm. So that's where you get your x squared dm from. Okay? because you're changing the deltas to dm's, and if you do that, you're just talking about integrating I. To be honest, this part here doesn't really make that much sense to me. Why does it change to di? But what I do know is when I integrate both sides, it just turns back into the I anyway, and we're just talking about all what we ever worry about is integrating the right hand side. Okay, so that's where the formula came from. Alright guys, next one we got to worry about is the parallel axis theorem. Okay, now just gonna press pause here for a sec. Okay, so the parallel axis theorem is basically if IC is the moment of inertia of a body of mass m, the full body has a total mass of mass m, okay, and about an axis c. So you're talking about how difficult it is to turn it around c, okay, through its centre of gravity. Now you're talking about the centre of gravity is the centre of gravity is where all the mass lies, okay, so it's through its centre of gravity, okay, so IC goes through its centre of gravity, okay. Then about an axis, then the moment of inertia of the body about an axis L parallel to C, so you can see L is here, okay, L is this line here parallel to C, okay, and there's going to be a different moment of inertia, because if you're not turning a body around its centre, it's more difficult to turn it around at different, like if you take it from a different point, but I'm rotating the pen this way, as opposed to from the centre, you can see that I think this is probably more difficult for me, okay? So, we're talking about a new moment of inertia that occurs because of L being different, okay, so L's moved away. Now, we want to prove that this formula is IL, the moment of inertia about the new axis that's parallel to the old axis, equals the moment of inertia around the old axis plus the mass of the object, the total mass of the object, multiplied by the distance squared, where d is the distance between the two axes. Okay? Now, it's worth knowing before starting the theorem proper that the variable r represents the distance between each piece of delta m and the axis c. So for example, this is r here. R represents, r could be any part possible. See if I move delta m, I also change the value of r, don't I? R changes depending on which chunk of the lamina I'm talking about. Is that alright? So r could be anywhere. If r equals 0, what does that mean? It's on the axis. Perfect, alright? Alright, I as usual equals the sum of, axis G. Okay, the distance between each piece of delta M and axis C, then R delta M. So you're talking about your radius multiplied by the mass you're talking about equals 0. This is because by the very definition of centre of gravity, the sum of all the moments about the gravitational forces on parts of the body about C is 0. So basically there's no turning moment around the centre of gravity. If your axis goes through the centre of gravity, then the sum of all the moments, see the way I have these two delta m's here, if I had another delta m down here, yeah, and another delta m down here, what they're basically saying is it will balance out and equal 0. There will be anti-clockwise moments and clockwise moments, and all of them will end up to be 0. Do you remember moment of a force is, what's a force by? Distance. Force multiplied by distance, and force is directly proportional to mass. So all the sums of mass by distances should be equal to 0, because by definition it is the centre of gravity. That's why this here equals 0. Once again, you're just going to be learning off and using it. Also, you guys need to know how to do is use the formula and learn off this theorem. Okay, so it's not a big deal, right, if you aren't fully comprehending it. Now, what's happening next is the moments on one side of C balance out those with the other side. That is what makes the centre of gravity what it is. Take a piece of delta m and let r be the distance from the axis. Its distance from L therefore is r minus d. So let's find out where r minus d is. R minus d, if I was to take this position here and this position here, that's the distance of just this random piece of mass I'm talking about away from the new axis, and it's r minus d. That's where r minus d comes from, okay, those two positions there. Okay, now we're going to do what we always do, we're going to find out our IL. Okay, so IL equals the sum of, now remember our formula, the sum of IL equals the sum of all the small pieces, okay, multiplied by the distance they're away squared. The distance is defined as r minus d squared. D is fixed, but r changes from point mass to point mass. We're talking about different masses in different positions throughout the body. That's why r is always considered to be changing. That's why we use the summation button. We're summing up all the r's and all the delta m's, okay? Now that that's done, okay, we're now going to multiply this out. We're going to square that out, and we're going to get r squared minus 2rd plus d squared, close bracket. Next one, we're going to break up into 3 different sums. The first sum is delta m r squared. The second sum is minus 2d. Remember, 2d is a constant, isn't it? And then it's going to be the sum of delta m r. And finally, the last one is going to be what's going to be d squared delta m. D squared delta m. Okay, first of all, what is delta mr squared? What is it? It's the same, it's the moment of inertia definition, isn't it? But it's the moment of inertia definition for the c-axis. Because if you take all this away, it's the c-axis that the point is a distance r away from. So that means you're going to replace that with IC. The next one is minus 2d. And what did we say about delta mr? What did we say about the sum of the moments around the centre of gravity? 0. Now that's your key. Starting off the axis from the centre of gravity, it enables us to eliminate this middle part, which is critical for the proof. Then finally at the end we're going to have d squared. Now what is the sum of delta m? Can anybody tell me? M. If I chop up a plane into tiny little pieces, then I add up all those pieces back together, I get back the plane in the first place. So if I chop up something into lots of tiny little masses, when I put all those masses back together again, they result in the mass. So that's going to be mass times distance squared, and therefore IL equals IC plus MD squared. Happy enough with that? Beginning. Alright guys, this one here is exercise 14b, question 2. This is a rectangular laminate. It has, find the moment of inertia about axis A. Now axis A has 2L either side. Okay, so axis A, this is this axis here. Okay, now they did get this one mixed up, because it's 2L to the left and 2L to the right. So what it should be is this. IA should be a third m bracket 2L squared. Now the reason I know this is I look into my tables, and it tells me that the moment of inertia about a plane is a third ml squared. That's for a length of 2L. This is a length of 4L. That means I have to double the L value to 2L. So now my answer is going to be 4 over 3 ml squared. IB, which is denoted in blue, has L to the top and L to the bottom. This will make it, it's a length 2L, which is what we learnt. So it's going to be a third ml squared. The next question is, find the axis through C perpendicular to the plane of the lamina. Find the moment of inertia through axis C. Axis C is not on the xy plane. It's basically the z plane. So we're going to use that theorem. IA plus IB. This is the perpendicular axis theorem. And this means that it's equal to 4 over 3 ml squared plus 1 over 3 ml squared. Add them together, what do we get? 5 over 3 ml squared. Yes. Finally, parallel axis theorem. The axis through P, now remember it's perpendicular to the plane of the lamina. Now where is P? P is located, sorry? P goes in the same direction as C. I underlined the key words there to explain that. P is here, C is here. What's the distance between the two of them? 2L. They're both parallel to each other, so we're going to use the parallel axis theorem. And the parallel axis theorem, as we just proved, is the new axis IP equals IC plus MD squared. IP therefore is 5 over 3 ml squared plus the mass of the object, which is m. What's the distance between both of them? 2L squared. Multiply that out, and what you'll get is 17 over 3 ml squared. Okay, part B. If a point mass of 3m is attached to the lamina at C, which one of 1, 2, 3 or 4 are increased and by how much? Okay, point mass of 3m is attached to the lamina at C. It's attached at the centre of gravity. Because the x plane, because x, y and z all go through this point, none of them are increased. The only one that is increased is P, because P is away from the centre of gravity. And remember, when you add on a new object, it's md squared. So you're adding on, 3m mass, is it? 3m times 2l squared. And that will add on 12 ml squared. Lads, try maybe 1 to 5 and see how you get on. Okay?